Hello, my dear students. Myself, Mr. Gundlewadi Gangadhar. First of all, I welcome all of you to the BSc second year third semester in analytical chemistry class. We are going to study the analytical chemistry. In that, we have to study the paper Instrumental Methods of Chemical Analysis, paper number 7. This paper will be taught by me. So we have to study this paper, Instrumental Methods of Chemical Analysis, first, paper number 7. This paper is for 50 marks. 10 marks is internal marks for your continuous assessment and 40 marks for university examination. Now we will see in detail what is the syllabus for this paper, what we have to study in this paper. As usual, in this paper there are 4 units we have to study. The unit 1 is of spectroscopic method, spectroscopic methods. In the spectroscopic methods, particularly, we have to study visible spectroscopy. In this unit, we have to study visible spectroscopy. What are electromagnetic radiations, how they interact with the matter, characteristics of electromagnetic radiations, then the theory of visible spectroscopy, what is visible spectroscopy, theory of visible spectroscopy, instrumentation, which instrument is used to carry out study the visible spectroscopy and its applications in detail. All these points we have to study in this unit first in the paper Instrumental Methods of Chemical Analysis first. The second unit, unit 2, again it is of spectroscopic method. In this unit, we have to study photometric titrations. Photometric titrations. What are photometric titrations? Theory of photometric titration, types of photometric titrations, instrumentation, and the applications of photometric titration. Again, in this unit, another point we have to study is AAS, atomic absorption spectroscopy. Theory of atomic absorption spectroscopy, the instrumentation, and the applications of atomic absorption spectroscopy. All these points we have to study in unit number 2. These two units are major for your syllabus, and the third unit is unit 3, electron microscopy. You might have heard the term electron microscopy. Electron microscope. So we have to study the electron microscopy. Again, there are two types of electron microscopy: scanning electron microscopy and transmission electron microscopy. We have to study transmission electron microscope (TEM). Again, in this theory, instrumentation and applications. The unit 4 is of atomic force microscope. Unit 4, atomic force microscope. In this also we have to study the theory of atomic force microscopy, instrumentation, and general applications of atomic force microscope. So this is the syllabus. These 4 units we have to study in this paper, Instrumental Methods of Chemical Analysis first, paper number 7 for this semester. Now before starting the syllabus, actual syllabus, we see generally what is the spectroscopy, because all these syllabus, all these 4 units we may say are related to the spectroscopy. It is related to the spectroscopy. And spectroscopy is the most modern tool in chemical analysis. It may be in analytical chemistry, maybe in organic chemistry, maybe physical or maybe organic. In all branches of chemistry, spectroscopy is the most modern tool for analysis. Now we must know what is spectroscopy. If we divide this word, then it is the spectro. Scopy means to see, just like microscopy, telescopy, etc. Scopy means to see, and spectro is a spectrum. It is a spectrum. Now, what is spectrum? That also we will see later on. But at this condition, you must remember, it is spectro means spectrum, scopy means to see. So, what is spectroscopy now? The spectroscopy is the study of interaction of electromagnetic radiations. Electromagnetic radiations with matter. Means the spectroscopy is the study of interaction of electromagnetic radiations with matter. Electromagnetic radiations, this is one term or one fact, we may say, the electromagnetic radiations, how these electromagnetic radiations interact with the matter. Study of this interaction is called as the spectroscopy. Okay. Now, when we study this interaction, then we must know what are these two electromagnetic radiations and what is the matter. What is electromagnetic radiation and what is the matter, that we must know. Then and then only we are able to know how they interact with each other. Okay. So, what are electromagnetic radiations? That we will see what are electromagnetic radiations, because these two are interacting with each other, electromagnetic radiations and matter. So, we must know these two in detail. So, what are electromagnetic radiation? So, the electromagnetic radiation is a form of energy. It is a form of energy. It is an energy that travels in space in the form of wave. So, the electromagnetic radiation is an energy which is traveling through the space in the form of waves. So, we may say the electromagnetic radiations are nothing but the energy waves. These are the waves. In general, we may say all radiations which are obtained from the sun are the electromagnetic radiations. There are different types of electromagnetic radiations. We may say gamma rays, cosmic rays, X-rays, etc. that we will see later on. At this time, we have to study what are electromagnetic radiations. These are nothing but the energy which is traveling in the space in the form of wave. Okay. Now, as its name indicates, electromagnetic. So, electromagnetic radiations are nothing but electromagnetic waves, we may say. Electromagnetic waves. As its name indicates, electromagnetic means that wave should have two components, electric component and magnetic component. Electromagnetic wave should have two components, one electric component and another is the magnetic component. So, the electromagnetic wave can be represented in this way. It is the direction of propagation. Say this is the wave like this. This we have shown one component. So, it has two components, electric and magnetic. So, I show by dotted by this colored line another one component like this. These two components are there in the electromagnetic wave, and these two components are vibrating perpendicular to each other. The direction of vibration is perpendicular to each other and the perpendicular to the direction of motion. For example, for suppose this is the direction of motion of this wave, direction of movement of wave. Wave is traveling in this direction from this place to this place. Now it has two components. One is a magnetic component. Suppose magnetic component is vibrating in this fashion, like this. In this fashion, magnetic component is vibrating. Movement of direction of movement is in this fashion. So this one and this one is perpendicular to each other. This is one component, and another one component is vibrating in this fashion, like this. Again, this direction is perpendicular to this one and perpendicular to the direction of motion also. So in electromagnetic wave, there are two components, one electric component and one magnetic component. These two components vibrating in a direction which are perpendicular to each other as well as perpendicular to the direction of motion. Now, how to characterize these waves? All the characteristics which we use, all the properties of wave which we use to describe a common wave is applied to this wave also. So the first we describe this wave as by wavelength. First we describe it as wavelength. Now what is wavelength? Wavelength is nothing but the distance between two successive maxima or minima. Wavelength is the distance between the two successive maxima or minima. Suppose this is the maxima of this one, this is second maxima. We may call it either crest and trough. This is minima for this wave. Again for this is the minima. Now distance between these two, this distance, this length is called as wavelength. Wavelength of that wave. This wavelength is denoted by lambda. Wavelength is denoted by lambda, and the wavelength is the distance between two successive maxima or minima of a wave. That is called the wavelength. Now, what should be the unit of this wavelength? As we indicated, it is a length. It is a length. What is the unit of length, or we may call it as the distance? What is the unit of distance? It may be meter, centimeter, millimeter, again smaller unit micrometer, again smaller unit nanometer, and angstrom unit, picometer, pm. These are the units of wavelength. Now we will see how these units are related. Suppose the wavelength is too much smaller, this distance is too much small, then we are not able to express in this meter. Suppose we have to represent 1 millimeter length, then it is difficult to express in meter because it comes to be 10 raised to power minus 3 meter, 1 millimeter. So instead of expressing in meter, we express it in millimeter. Suppose we have to show the distance between two cities. Distance between two cities. So we represent as in kilometers instead of representing in meters. So for our convenience, these are the smaller to larger units of wavelength, which we will see now. What is angstrom unit? One smaller unit. Picometer generally it is not used to represent the wavelength. Picometer, just we will see what is picometer also. 1 picometer is equal to 10 raised to power minus 15 meter. Then somewhat longer unit of length is angstrom unit. 1 angstrom unit is 10 raised to power minus 10 meter. Again somewhat longer is nanometer. 1 nanometer is equal to 10 raised to power minus 9 meter. Then micrometer, 1 micrometer is equal to 10 raised to power minus 6 meter. Again there is millimeter is equal to 10 raised to power minus 3 meter. Then we have centimeter. 1 centimeter is equal to 10 to the power minus 2 meter. Then meter, so etc. These are the units of wavelength. According to our convenience, we use such units to express the wavelength. Okay. Now this is the first characteristic of wavelength. Now next we describe wave. You might have familiar this word frequency. You might have heard this word so many times. Frequency. What is the frequency? Frequency is nothing but the number of time. Same thing repeats in particular time. That is called frequency. For example, suppose we are going to college for 3 times in a day. So we made our frequency to go college is the 3. That is the number of times, number of repetitions of the same thing. That is called the frequency. In case of this one, we may call it as the number of waves passing through a point per second. That is called frequency. Frequency is the number of waves passing through a point per second. That is called frequency. Frequency is denoted by nu. Frequency is denoted by nu. Now, what should be the units of frequency? In simple one, we call it as CPS, cycles per second. From this place to this place, when a wave travels from this one to this place, it is called one cycle. It is called one cycle. One circle. Suppose this is a circle. At this place there is your college, and at this place there is your home. You come to college, again go to home. We complete one cycle. Same way it is from this place to this place. There is a one cycle at same position. So it is the CPS, cycles per second. Common one. Again we use hertz as a unit of frequency. We use hertz as a unit of frequency. What is 1 hertz is equal to 1 cycle per second. 1 cycle per second is equal to 1 hertz. Again, higher units are kilohertz, megahertz, gigahertz, etc. For your mobile phones, the speed of your microprocessor of your mobile is given in hertz, megahertz, gigahertz, etc. So that is the cycles per second. It is unit of frequency or hertz. Higher units are kilohertz, megahertz, gigahertz, etc. Okay. Now we will see how wavelength is related to frequency. Now what is frequency? Number of waves passing through a point per second. Number of waves passing through a point per second. And what is wavelength? Distance between two successive crests or two successive trough or two successive maxima or two successive minima. For example, I will draw this much wave here, like this. Like this. Okay. The distance between this one to this one. The distance between this one to this one is called as, this distance is called as wave. This distance is called as wave. Okay. Now this length, suppose we consider it as 1 centimeter length. So the wavelength is 1 centimeter. Okay. Now frequency is, suppose we are taking, this is 1 point. This is 1 point. Now we have to measure how many such waves, 1 centimeter length waves, pass through this point in 1 second. Okay. That is the frequency. Suppose this 1 centimeter length is passes through this point only one time in a second, then the frequency is 1. If it is passing 2 times in a second, the frequency is 2. Okay. If it is passing through the point 3 times, then it is frequency is 3. Likewise. Okay. Now, how this relates with the frequency? What will be the effect of wavelength on this frequency? When we increase the wavelength, what will be the frequency? If we decrease the wavelength, what will be the frequency? Okay. Now, firstly, we will see now. Suppose the distance. Suppose this is the college. This is your home. This distance is suppose 1 kilometer. Okay. Now you have to say that only you have to go to this college, go to your home continuously in during 1 hour. During 1 hour. Okay. So how many times you go from home to college, college to home? That we have to measure. Now this depends upon speed of your walking or your bike or your cycle, whatever may be your vehicle. That depends upon your speed. If we keep this distance constant, this is 1 kilometer distance, and suppose the speed of your bike is 2 kilometers per hour. So to complete one cycle, you have to travel how much distance? From home to college, 1 kilometer. From college to home, again 1 kilometer. Means total distance you have to travel 2 kilometers. Total distance you have to travel 2 kilometers, and your speed is 2 kilometers per hour. Now to complete one cycle, you will require 1 hour. In 1 hour, you complete this one cycle. So your frequency is 1. Suppose we have increased your speed. We have increased your speed. Suppose your speed is 10 kilometers per hour. Then how many cycles will be completed in 1 hour from college to home, home to college? Total distance is 2, 10 by 2, 5. So your frequency becomes 5 now. So as your speed increases, the frequency is also increasing. Isn't it? When we increase speed, the frequency is also increasing. Now, in case of electromagnetic radiation, just like speed of light, we know speed of light is constant. So, the speed of electromagnetic radiation is constant. Now, what we will see what happens when we decrease this distance. Suppose your speed is 10 km per hour. Now, we have decreased this distance from 1 kilometer to 0.5 kilometers. Now you have to complete 1 kilometer distance from home to college, half kilometer, college to home 1 kilometer. Again half. Total 1 kilometer distance you have to complete for one cycle. And your speed is 10 kilometer per hour. Then how many cycles will be completed in 1 hour? That will be 10 divided by 0.5. It becomes 20. 10 divided by 10 divided by 1, wavelength is 1, 10 divided by 1, 10 cycles. So when we decrease the wavelength, frequency is increasing. When we increase wavelength, suppose this distance is 2 kilometer, then frequency becomes 5. So we may say the frequency is inversely proportional to wavelength. As wavelength increases, frequency decreases. As wavelength increases, frequency decreases. Wavelength decreases, frequency increases. As we shorten the wavelength, frequency will increase. As we increase the wavelength, frequency will decrease. So this is the relation. We may say now the frequency is inversely proportional to wavelength. Frequency is inversely proportional to wavelength. Okay. Now the third term which we use to describe a wave or characterize a wave is wave number. It is denoted by mu bar. Now wave number is the number of waves per centimeter. Number of waves per centimeter. We have to take 1 centimeter length. Suppose this is a 1 centimeter length. Then how many waves will accommodate in this 1 centimeter length? That is called wave number. Suppose wave is like this. From this one, 2, 3 waves are accommodating in this 1 centimeter length. So we may say wave number is 3. Okay, suppose wavelength is 1 millimeter, 0.1 centimeter is the wavelength. Then what would be the wave number? Wave number will be 1 divided by 0.1. That is 10. So the wave number will be 10. If wavelength is 0.2 centimeter or 2 millimeter, we may say, then the wave number is 5. Again, wave number also relates with the wavelength in inverse direction, in inverse relation. Wave number is inversely proportional to wavelength. As we increase wavelength, wave number decreases. As we decrease wavelength, wave number increases. Now, what would be the unit of wave number? Unit of wave number is simple, per centimeter. Because we are taking per centimeter. In 1 centimeter length, how many waves are there? That we have to concern only. So the unit of wave number is per centimeter. Now we have said the electromagnetic radiations are the energy. It is a form of energy that travels through space in the form of wave. Now it must have some energy. It may be greater, may be higher, etc., etc. Then what would be the energy associated with this electromagnetic wave? That energy is given by energy of wave E is equal to h mu. H is a Planck's constant, mu is a frequency. Means the electromagnetic radiations, energy of electromagnetic radiation relates to the frequency. Yeah, H is constant. So we may say E is proportional to mu. As frequency increases, energy increases. As frequency decreases, energy decreases. Okay. Now what is nu? Nu is c by lambda, speed of light divided by wavelength. Nu is speed of light divided by wavelength. So E is equal to h c by lambda. Again, energy is depending upon the wavelength, because h is Planck's constant, it is constant. C is the speed of light, speed of electromagnetic radiation, it is also constant. Now how energy varies? Energy of electromagnetic radiation varies with wavelength. So these are the characteristics of electromagnetic radiations, electromagnetic waves. Now we have to see what is the spectrum, what is the spectrum and the energy of these electromagnetic radiations. After arranging the spectrum, we will see in detail. So we will stop here. Thank you.